Hello, everyone. Hope everyone's having a good time out here, learning more and more, specifically about how we can all help with your projects in the realm of motion controls and robotics. I'm John Yampiro, regional manager for AMC for the past 12 years. Actually moved from New York all the way to the West Coast, and that's where we're from. Okay. Maybe it's the other way. Technical difficulties. Thank you. I think my colleague set me up. That's what I think. I'm only going to do a few slides. Just want to give you a basic overview because the technical portion of this presentation is going to deal with robotics, which is the primary subject here. However, many of you may not know AMC. So AMC is Advanced Motion Controls, and our home base is headquartered. We're vertically integrated, and we do everything out of our facility in Camarillo, California. Now, most people say, well, where is Camarillo, California? So the logical response is, say, 45 minutes either way in between Santa Barbara and LAX or downtown LA. And they go, oh, okay, I have a pretty good idea. But now another way to say it is to say 2.5 hours from wine country in Paso Robles, or right up the block from the institution Ale House. And, you know, then they like that location as well. So we house everybody and all of our product in a 86,000 square foot facility. And it's a co-owned company, so we're privately owned, co-owned by Daniel Schoniewald, and he pretty much runs the entire operation in Camarillo. And his partner, Shandor Barta, operates out of our Budapest, Hungary facility, where we do advanced machine controls and additional servo drive sales. We're really known as a servo drive manufacturer because back in 1987, when we started out as a company, it took that very first sale to launch Shandor and Daniel, with Daniel's wife, out of the kitchen and into their first office building. And it was a contract that we received from a company called Remotech, now owned by Northrop Grumman. And it was for a robot, which today is known as the Andros robot. And this robot does bomb detection. So our first order that put us on the map was for traction and articulation drives that operated the Andros robot. So what we learned from this was the only time our drives fail is when the bomb blows up the machine, but otherwise we're pretty good. Other applications just to be aware of, because we're so diverse in our applications. So some of the other projects, we were the first servo drive to be on the Da Vinci surgical robot. We were the first drive designed into that. We were the first drive designed into the Kiva warehouse robots. We were the first drive to be designed into the Segway. We were the first drive to be designed into the wheelchair that went up and down stairs. And, you know, kind of the list goes on. It's very amazing. Everyone here is somehow related to the robotics industry, and part of the excitement of what we do is the robotics industry is very exciting. And so that's why I've been in it for so long. This is sort of a timeline. So 87 is where we received our first contract, but of some very more important notes to make. We started out with analog drives, and analog drives receiving all sorts of inputs, plus or minus 10 volts, step in direct, PWM in direction, step in direction, We also made a sine drive, which is a hybrid, which is actually a sine wave. It gives you sinusoidal motion, but the loops are analog. We came up, we were like kind of like in the forefront of developing server drives with analog loops. But then as technology advanced, we came into the digital realm, and we provided digital drives. And one of the landmarks of that was we provided our DX series, which is a can open, back in the late 1990s, supporting a company called GE Medical. And we then took it on, and I would say in the middle of 2000, say 2007, 2006, we launched our EtherCAT drives with a company called Philips Medical. The reason why I bring these two sort of milestones up, it was with these companies that we utilized a network and provided a specific solution to their robotic machines that were applied in applications where it was so critical that the drives had to be reliable, they had to be performing, they had to be very low noise emissions, and AMC came up with that solution. So AMC, how we promote ourselves is we're more of a solution house. And so up until, I'm going to let Chris go into it in more detail, but our solutions is going to be first partnering with you and your technical team to come up with the best total machine control solution together and implementing it. Or in my case, coming up with the best, say, servo electronic solution and then delivering it. So we do have a wide variety of product technology, and it's such a wide breadth. It goes from a fraction of an amp down to 10 volts, up to 250 amps, and up to 800 volts. So then we'll do 460 volts AC. But the thing is, what you'll note from what I'm about to tell you is you could go to our website, and it's very informative, and it's pretty nice, fairly intuitive. But the thing is, there's probably over 50% of what we can supply you that's not listed there. The reason being is much of our features that many don't know about are custom generated, and we don't put all of our, we can't. We don't put our custom products with specifications online. So I bring this point out only because if people are interested in servo solutions and it's not listed in our website, don't think we cannot do it. Come to me specifically, or Electromate. We work very closely with Electromate, and we will go through the entire applications, what the requirements are, what you're trying to achieve, how many units are you going to build, what's your price target. Being a family-oriented company, we partner with our customers. We can't be everything to everybody. So even though we have standard product that's very diversified, typically in special robotic applications, we'll start with standard product. We'll prove the concept, the machine works, right? Then we have the next phase of the design, and we sit down and we say, well, how do we optimize the design? Maybe we take electronics that you have and put it on our board. Maybe we pull electronics out of our design because it's overkill and you don't want to pay for what you don't need. So that's what we do. We have a series of Digiflex Performance, which is our digital series drives. Accent is our analog series drives, and the custom solutions are what I was just talking about. Click and move is what Chris is going to get into. I look at it and I present it as it provides functionality of a PLC, a motion controller, a process controller that includes vision. It's got built-in graphics, built-in HMI, built-in safety, all for the price of less than the motion controller. And it's a really nice alternative for OEM style machines. We also provide mounting cards, power supplies, so we'll handle the AC to DC. We can put in our plug-in drives. We can add power correction factor technology. We can boost up the signal. We're very capable. We also promote ourselves as being everything to everybody. So when you go even onto our website, we have a third party, a third, like, joint venture third party collaborative. And many of the other presenters that are here today are also listed in that part of it. So we work very closely with many motor manufacturers, many feedback devices. It's pretty much any network, any controller, any environment. We provide the solution working, and we keep ourselves very flexible to be to work with companies. So some of the things we can do is the products that are, as I said, they could be packaged AC to DC, or they can be plug-in solutions. We can put servo drive axes together on one board. We can embed these drives inside of motors. We can, okay, some of them go into robotic joints, so they're very diversified. Okay. So just to list a few of the networks that we are working with, that would be Modbus TCP/IP, EtherCAT, PowerLink, CANopen. We actually still support SyncNet, all the serial, and we work with various controllers, various actuators, various other technologies. As I had mentioned, just to give you a flavor of all of our products that we manufacture, 33% are custom. And custom in a sense that if I have a regular servo drive and you tell me your robot is going to be working inside of a refrigeration, we would say, hey, go to our extended environment drive, and we could support that. However, if the volume is so critical and the cost is so critical, well, what AMC will do, which is different than most companies, AMC will say, okay, let's just change some of the components that are going to operate at that temperature. It's pennies on the dollar, couple of bucks NRE, and then we're off to the races, and you're only paying for that part of the design that you need to operate. So you didn't get the whole full military, the full extended environment features. Only the features you need are the ones that we're going to supply you with and keep you as cost effective for your volumes as possible. This here is the custom 3-axis EtherCAT solution that we do for Philips, and these are all representation of the customization that we do. So the first kind, where there's no PC board change, it's 33%. The second kind, which is also 33%, is from a clean sheet of paper, and that's where we're at. And with that, just to give you a flavor, as I said, we were vertically integrated. All of our manufacturing, highly automated, is done in our plant floor. And in our plant, our return rate is approximately 0.3%. So you say, oh, that's good, but that's not great. But when you think about 67% of your product is customized and not what you build standard constantly, 0.3% is pretty good. Our on-time deliveries are 97%, and we work with you on dates to pull them in or put them out or however we need to schedule that. So we're a very flexible company. The neat part that I really love about the company is you will call in and you will always get a warm body, and that warm body will send you to the right place. And if it's a technical question, we have a team of product development and applications engineers that are going to answer your call and support you. And then if it turns into a project that we've got to get more intimate, we bring in our engineers that are in-house. So just to give you a flavor, we're about 140 employees strong. Of the 140 employees, 70 of these employees are degreed engineers. Of the 70 degreed engineers, 30 of them are design engineers, which is kind of unheard of. If you think of that percentage, almost a quarter of the percentage of your people, design engineers. That's because of who we are. That's because we do 67% of customization to give you the best final solution that you're looking for. We constantly keep our doors open to all of you. So anytime you're on the West Coast, You want to go with your families to Disneyland, feel free to come visit the factory. As I mentioned from the very get-go, we've got 30 years experience in electromechanical design and 30 years experience with respect of firmware knowledge and application. And we're always looking forward to becoming more understanding of our customers so they can see how we operate. And essentially, we become an extension of your group. Here's some of the certifications. The CE, UL, ULC, RoHS compliant, REACH, ITAR, and we're an ISO 9001 organization. Our initiative has always been, we don't want to be the biggest, we just want to be the best. And that best is essentially extending ourselves to supporting our customers. And that is critical when you're working on projects and you have to, and you run into some technicalities. Sometimes we get calls in and say 30% of the calls have nothing to do with our server drive. It's the interaction between how the server drive is operating in the system, but we don't care. We're going to work with you through whatever your issues are, and we're going to come back and get you responses regardless. And that's all part of the AMC team. And some of the things that we do, if you're hearing noise, or let's say, for example, you're using a Maxon motor, and this is the perfect motor for the robot, but it's got such a low inductance, then rather than say, oh, but the standard doesn't do the inductance, we said just send the motor over. AMC is going to run the drive with the motor. We're going to change some parts to optimize the current loop tuning, and then we're going to send it out, and now it works. That's the type of service that we just give normally to all of our customers and making sure that you've got the proper performance. And we work worldwide through a rep and distributorship. Like I said, Electromate doing a great job for us for over 23 years. I'm working with them for 23 years, so it's probably more. So that's the final lab shot here, snapshot. Any motor, very universally applied. I'm going to leave it now to my fellow Chris Fournier, who's going to get into the technical application of the design, of the controls group, I should say. If anyone has any questions, feel free to come by after his presentation and we can discuss specific applications and specific technicalities. I wanted to say we were on SpaceX launch, but we weren't. We were on Rocket Lab, and that was pretty cool too. You're good.
Okay, are we working? Good, 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 good. Okay, one thing I'll guarantee you. 2:45, we're going to be done. Up until now, we've been hearing about hardware. So we're going to turn and make the jump to Lightspeed. And most of this presentation is going to be dealing with software, control systems, and how you put them together. The title of this presentation is called Open Standard Tools for Robotic Control. We're going to be concentrating on 3 standards: XML, PLCopen, which will occupy the majority of this discussion, and ISO 6983, which in the States is ANSI RS 274. For those of you familiar with it, it's the G-code language. So I'm going to be starting from the top, generically, broadly, and we're going to whittle all the way down. You'll see some code, and at the end of this presentation, we'll actually run the project. We'll actually run a simulated 3D printer based around a linear delta robot. So late 1980s, right at the fall of the Soviet Union, there was a professor, Dr. Sam Milstein, out of the University of Leningrad. And he was an applied physicist working on semiconductor crystal manufacturing processes. And he had an idea about how to build control systems. He wasn't a control engineer, but for the group around him, he tasked them with coming up with a way to graphically represent how software, pieces of software, could control machines. Because up until that point, particularly in the former Soviet Union, most of the control systems were discrete pieces of electronics. So he pioneered, today it's given various monikers, but today we would call it component-based software engineering. And essentially what we mean by that is the idea that project code can be developed by literally taking pieces of code that are represented graphically and hooking them together. Think of an electric schematic, an electronic circuit board, and what does it do? Why did he want to do that? The reason being was that he had software engineers and he had people designing boards, but he didn't have anyone there that understood the process. And if he could come up with a way to teach somebody how to program the process, if they understood the process, that was a real home run, if he could make it intuitive. Well, as you all know from history, that year in '89, the Soviet Union fell. Things went apart. Not a lot was done about this idea until probably mid-1990s, late 1990s. We'll get into that. But part of this component-based software engineer was the component. What are we going to define a software component as? It's a system element. It's a piece of code. Whether it's written in a textual language, a graphical language, it does something that's been predefined. It accomplishes something, and it also communicates with other software components. And it's written to a specification. This is important. It's written to a specification. One type of software component, one which we're going to pull on for this discussion and for our open architecture control system, is called a function block. The function block, at least as described by the PLC language standard, IEC 61131-3, is a software component that's the lowest level. It's the basic building block of your code. And the code could be process control, sophisticated robotics, and everything in between. In our case, and in the case of PLCopen, the function block is actually implemented as a C++ class. And for expediency's sake, I can't show you the extensive class library for PLCopen. We're gonna see a snippet of it here. For those of you who are interested or have projects, we can talk about it. I can show you the library. But there's an example here in front of you. And it's basically a function block. Looks pretty generic enough. What does it do? It sets up a kinematic transformation. It doesn't mean the kinematic transformation's been defined, but it actually sets that kinematic transformation. And it pulls the hooks together for other logic that is associated with it. So our concept now consists of component-based software engineering. We're going to use components that are called function blocks. We're going to do so to create an application program, and we're going to use a visual icon-based programming language. We've got to get some definitions under our belt, though, to start. I mentioned the presentation is based around 3 open standards. One is XML. Probably a lot of you are familiar with XML. Probably some of you have written pieces of code with XML. But for all intents and purposes, as it says up there, it stands for extensible markup language, similar to HTML. Primarily, XML was designed to do 2 things: store and transport data. And for all intents and purposes, XML is just information wrapped in tags. That's all it is. Second of all, PLCopen. PLCopen in 1992 was started much to the consternation of automation and control system vendors. And the reason it was done was increasingly, whether it was a PLC in the traditional sense of a rack-style PLC, or whether or not it was something that was proprietary, single board, layered board, it didn't really matter. Increasingly, software was becoming the key component of controls. It wasn't so much the hardware. It was how you programmed your hardware. And what was found was you could buy controls from Hitachi, Armron, Panasonic, Rockwell, Siemens. It didn't really matter. And everyone claimed to say, well, our language is very similar. You should be able to program it. Well, it really wasn't. So this organization was started to support both vendors and products that was going to be independent of a sales process. It was really going to determine what these languages, for lack of a better, what the structure of control software was going to be. And as it says there, it was focused around the International Electrotechnical Commission standard that had already existed. And they defined 5 languages. We won't go into those here. Suffice it to say that function block diagramming was one, sequential function chart, structured text, instruction list, and there were 1 or 2 others, some of which have died away. What PLCopen did, however, that gave the University of Leningrad and Dr. Sam Milstein something that didn't exist was the class libraries that could be represented graphically. That was the key. Not only those class libraries were independent now of platforms. And I'm going to stick my neck out here. What I'm going to show you in the short amount of time here with the sample program, the project that we're going to run and how it's constructed, it doesn't matter what I constructed it on. Could be a Windows PC, could be a Linux PC, it doesn't matter. I can run that on a Linux platform, I can run it on a Raspberry Pi, I can run it on a Windows 10 operating system, and just about everything in between. Lastly, ISO 6983, all it is, for those of you who are involved in numeric and control, CNC machining, it's G-code language. That's all it is. Some more definitions to finish up. A linear delta robot. Basically all it is, it's a parallel robot manipulator in which you have 3 sliding joints. It's not a serial articulated robot, and you'll see an example of it here shortly, with each one of those joints having 1 degree of freedom, and they move separate arms, meaning they translate them linearly, and they connect to a single plate at the bottom. 2 other definitions really quickly. Forward kinematics. All it is, once again, a system of equations which you use to determine the end effector's position of that robot based on the position of the actuators. Inverse kinematics, instead, are equations used to calculate the necessary actuator positions to move the end effector to the desired position. One equation, sets of equations, comes at it from this way, the other comes at it just the opposite. Okay, let's start drilling down now. Let's look at a mechanical model. On the left-hand side is a stylized drawing of what I just described, a linear delta robot. You've got 3 columns. They're spaced, in this case, 120 degrees apart. The carriage positions can be defined. The triangle instead is a circle. They're attached by movable joints. And you have potentially some offset depending on what you're doing. In our case, we're going to be talking about a 3D printer. It could be a plasma cutter for all I care. Doesn't matter. The model stays the same. And on the right-hand side, you have now starting to come together in the real world. Well, what does this thing look like? What is this Delta robot actually going to do? And as I said, you have a filament going down through. There's a heated nozzle. There's an extruder axis you have to control. And by the way, even though it's not going to be shown, we would be controlling the actual heating element, controlling that approximately to 1/10 of a degree Fahrenheit. Okay, so what are the challenges and the constraints? What are we up against? You're supposed to be using standard tools to solve that problem, a real world problem, create a 3D printer. So what are we up against? Well, we were told you have to use PLCopen function block class libraries to configure and create the control logic. It has to be the heart and soul of the control logic. Second of all, and this is key, it opens the door to everything. I don't care if you have a SCARA robot, an HBot, an articulated robot arm, I don't care. The process and the software tools are the exact same. And if you have anything in that process where you're controlling the robot that's peculiar, maybe you have some algorithm, maybe you have to sync with a slight offset the extruder position related to the vector velocity. I don't care. If you can describe it and you can create an algorithm around that, you can use it. Because the other challenge we had, and we were lucky, PLCopen states, not only do you get our function block class libraries, but we have a rule. And what does the rule say? The rule says, open up an empty function block, give it a name, stuff your C++ code on it, save it in the library, it's there forevermore. And that's what that second line does. It allows for custom C++ code to be used and embedded in the control logic as needed, which means all of a sudden now the sky's the limit. All of a sudden now we create a graphical object, the function block. It can have anything we want in there. We also had to use G-code. Well, why G-code? What was so special about G-code? Well, this control architecture happened to move into the arena of robotics. It also happened to move into the arena where robotics were used in conjunction with other control scenarios, both discrete manufacturing and process control, and G-codes in those particular industries were used quite a bit. In our case, for those of you who know anything about 3D printing, whether you're going to be printing from plastics, plastic algorithms, plastic amalgams, or even powdered metal, for instance, slicing programs spit out G-codes. So if you can't manipulate G-code file, you're not going to be able to control the process. And then finally here, we were up against the ability to synchronize and integrate an extruder axis. So what's the solution? How do we do this based on the tasks that were in front of us? Well, we created a graphical programming environment with a logic schematic editor. You're going to see a piece of that here shortly. We use standard PLCopen function blocks to create the logic for the different states and the kinematics. We created XML files, and we made them available through this integrated development environment, which you're going to see a piece of also. And then we created a user-defined function block to handle the Delta robot kinematics, and we stored it in our common library now. So what does that mean? As I said before, we encapsulate C++ code in that user-defined function block. It's in robot handling library. So are the kinematics for a SCARA robot, as I said. Articulated robot, 6 degrees of freedom. How many of you have watched a soccer game and or the Super Bowl? I would hazard a guess probably everyone in here at one time or another. And if you've seen, probably not, unless they screw up somehow, the camera actually follows the action on the field, whether it's a soccer stadium in Europe or Asia or the Super Bowl in the United States. Well, how do they do that? There's a company called Cable Cam. It's a glorified robot, 6 degrees of freedom. They've got these big drums, rotary axes, controlling the position of the camera. Similar to the Delta robot. We have a kinematic model for that because we're the ones that did that. And then finally, we had to create a user-defined function block to translate the G-code commands into PLCopen motion, and we had to store them in a database. For all intents and purposes, what does that last line mean? It means we had to come up with a G-code translator. Once it's done, it's there forevermore. It's called a motion task. It's available to anyone who takes advantage of it. Let's drill down even more now. Let's take a look. I said that we created function block diagrams. For time's sake, we cannot look at every one of those function block diagrams in this project. But what I will say is this. Importantly, the one highlighted in yellow, called main, is the heart and soul of any project in our development environment. What it does is it pulls together any of the sub-schematics or any of the adjunct schematics, and it says, okay, you should be able to print that out, take a look at it, and you should be able to pull somebody off the street and look at that because it's self-documenting and it's graphical. It's the heart and soul of the development environment. But the ones for this presentation that we want to talk about are the running state, process G-code settings, and the robotics axis group. That's the heart and soul of the robotics and the kinematics for this presentation anyway. So let's take a look now at that robot axis group schematic. There it is right there. I can print this out and I can give it to you, and I will guarantee you after the next slide, you're going to have a pretty good idea of what's going on there. What you won't see, you're going to see a snippet of it for one, but behind every one of those function blocks is C++ code, standard and C++ code. You don't have to know C++ unless you want to write your own function blocks. So what have we done? We've encapsulated the C++ code in the function blocks, and we can compile all of this for the hardware platform you're going to run on. We're going to run on this Windows 10 system. So let's take a deeper look now. Let's drill down even more. Let's find out what essentially that left side of the schematic does. Because those three function blocks, top to bottom, are the heart and soul of the project. And that's what it does right there. As they would say in The Wizard of Oz, don't pay attention to this and this, because you're looking at it and say, well, geez, that's an articulated robot arm. That's not a Delta robot. It wasn't meant to represent a Delta robot. What it was meant to do in this diagram is to show you the different coordinate systems so that it would be easily explained in terms of what those function blocks do. The one in the upper left corner called axis group reference, what does it do? It sets up what the axes are. It groups the axes and said, here's my group, X, Y, Z, A, B, C, with an extruder axis. It depends on your coordinate system. You'll notice under properties, there is a small little strip on the bottom of that function block that represents an XML file. Every time you see a property moniker on that function block, it means that it's getting its characteristics from an XML file somewhere. Oh, and by the way, when all of these schematics are created and you create these, we automatically create the XML files for you. You get to poke those values there, but you don't have to go on your own and create the XML files. So, as it says there, that robot delta function block generates the kinematic transformations between the axis coordinate system and the machine coordinate system. Inside of it, we're going to see it on the next slide, is the actual C++ code, or some of it, that actually handles the algorithm for the kinematics. Right below that, we have another one. Well, where does the Delta robot, after you handle the axes and you translate it into the machine now, where does it go from there? What is that model? Our model for this example is a triangular pyramid, an inverted triangular pyramid in the Cartesian system, X, Y, and Z. So the second function block handles the transformation between the machine control system now and the part coordinate system. And then lastly, in this case, when we actually have the extruder nozzle on it, in our example it doesn't exist, but we go a step further and we say the tool coordinate system now gets changed into the machine coordinate system. Axis group, coordinate system, machine coordinate system, transformations, and then here, how do these relate to each other? Pretty straightforward for all robotics. Doesn't really matter. You have to go through that process for any robot system you control. Okay, I mentioned in the prior slide that there are XML files that are used to configure what code is in that function block. This is an example of the delta function block, kinematic function block, and you're seeing two views of it. In our development environment, we put a nice wrapper around it, pull down menus, and make it easy for people to use it. We also provide, once it's generated, the XML file, which you can open up. In this case, it was opened up in Microsoft Visual Studios. Okay, let's drill down even more. Let's look at the function block, the heart and soul. I told you it was C++ code. Very first thing you're going to find, for those of you who program in C++, are the contents of a header file. It's just variable declarations for the parameters to handle the calculations. And then finally, because I couldn't expand it out and make sure everyone would see it, would be the C++ file, the actual source code that gets compiled. And you'll see a snippet of both the inverse kinematics and the forward delta kinematics. If you program in C and you've done lower level C++ code development, this can be attractive. As I said, there may be some things that are very particular for what you're working on. Maybe not. I would hazard a guess, we don't have time to discuss it, but I would hazard a guess that most of what you've had done, if you're working in robot kinematics, robot coordinate systems, we've done already, and they already exist either in our library or the PLCopen library. Okay, now let's take a look. What about G-codes? So all of a sudden now we've created a model. We understand physically what we're up against. Where do we go? What moves the end effector around? The G-code file. How do we handle the G-code file? It just doesn't magically get changed into motion. So there is a G-code file, a .nc file, which generally is created by a slicer program for 3D printing or a CAD/CAM program in the standard discrete manufacturing world. So that G-code file has properties. Initial register settings, how many axes, any constraints on the axes. That's brought into another block. So we take the settings from the XML file and we process them. We process the G-code file. Here's our G-code converter. Once again, you don't have to do it. It's done for you. It takes that G-code line by line and it converts it into a generic text database. And it makes it available to you. That file, once it's converted, is there. And you'll actually see it on the little operator interface we're going to bring there. Once this is generated, that motion task, this file gets fed into what's called the CNC running state. That's a whole nother schematic. Don't have time to go into it. Can certainly send you this project and all the details of it. That gets executed line by line at the speed of the hardware platform that it's running on to actually run the path that either the CAD/CAM or the slicing program for this Delta robot arm has created. In this case, the G-code handling function block also has an XML file, very similar. In our little wrapper, in our IDE, we talk about what type of motion is it? Do you support arcs? Is it a bunch of line segments? What are the axes that are set up? And this is kind of a raw look at that same thing in Microsoft Visual Studio. Okay, here's where it all comes together. We're coming to the end of this thing, and I'm not even at 45 up. Good. Along with our schematic editor is an integrated operator interface that's built in. So one thing that you'll see is a representation, a 3D representation. You're going to actually see this running here shortly, And then the G-code file that you can load, and then the database, this motion task that translated the G-code file into PLCopen line-by-line statements. And by the way, you'd say, well, what if I have an M code? For those of you who know G-code, I want to go off and do something special I created on my own. We don't care. Describe to us what it is. We'll incorporate it into the XML file. It's there forevermore. And this doesn't have to be post-process. Because some of you may be thinking, whoa, wait a minute, you know, he just said that this gets translated into PLCopen motion commands, and I could run it on this box, I could run it on a Raspberry Pi, I could run it on what I wanted to. The answer is yes, that's correct. Because we give you the compiler to do that. And we have a variety of compilers for the hardware platform that you want to run on. Okay, let's take a look at this project. Let's actually run it. I'm going to back out of this. Just bear with me. You'll see some axes come up. Trying to get this posted. I may have trying to run that on that, but do I need to kill? Okay. Hopefully you can see that. That's not too blurred. Same screen, but now it's actually controlling a 3D printer based on the project that we had. So let me give you a different view of that. So we're gonna move this through a slightly different angle. Okay. So if this was connected to a real machine, and by the way, everything you're seeing here, the only difference is the XML file. The XML file, and unfortunately, I apologize, you can't see the two other axes here. The XML file says, oh, these are virtual axes. They're executable files for the purpose of this presentation. If you go in, and I can show you where it is, you poke the XML file and say, oh no, I want to use 3 CAN open axes, or I want to use 3 EtherCAT, or 4 EtherCAT, or 6 EtherCAT axes. You describe what they are, and instead of running it on the screen, if we had the hardware in front of us, we could run the actual machine. That's the only difference between running it here and running it on a real piece of hardware, on a discrete machine. Code doesn't change other than that. So what would I be doing now? Well, I hit power. In our case, it enables the axes. If I was hooked up to a real piece of equipment, I'd be enabling the servo drives. So now I'm going to tell it to start. And you'll see it running through. Unfortunately, I apologize. The other 2 axes aren't here. You'll see the actual drive position on the servo drives, the axis coordinate systems, the machine coordinate systems, and the part coordinate systems. It runs down line by line at the same time that it's already pre-processed this, and it's showing you the corresponding ones. The velocity of this process can be handled 2 ways. You can hard code it, velocity, acceleration, deceleration. If you're using a G-code file, generally the slicing program handles all that, sets a feed rate with an F value and some M values. And it's going to finish. The only thing for the purposes of this presentation that you won't see is the extruder. I'll finish by saying we've done this for 3D printing robots. We've done this for SCARA robots, HBots, articulated robots cable cam robots. It's a very flexible development environment. It's based on open standards, and it's based on a user, an integrator, an OEM, having the ability to go and tweak that now for their uses, his or her needs. So with that, unfortunately, I'm 5 minutes over. I apologize, but if you have any questions, more than happy to answer them. And I will also, offline at the end, will be around to answer any questions. So hopefully it gave you a flavor for the open architecture control system. And that's it.
Technology has long been a disruptive force. During the 19th century, the Industrial Revolution altered the world profoundly and permanently. During the 20th century, mass production and electricity reshaped manufacturing, giving rise to large, slow-moving global manufacturers. Today, there are new forces at work, and they're changing the world around us, especially in the field of automation. Thanks to technology, the most successful and disruptive organizations consist of a small nucleus of people with a BHAG, a disruptive technology, and a laser-focused strategy. Today's innovative machine builders and robotics trailblazers are leaping ahead of the competition by thinking big and acting nimbly. As an automation disruptor, understanding what products to integrate into your machine is critical to your success in the 21st century. But with so many emerging technologies, chances are you need someone to help lead the way. That's where we come in. At Electromate, we spend our days helping manufacturers like you build better machines. This is why we exist. Electromate has dedicated teams made up of the best mechanical and electrical engineers in the field. We work in harmony with your engineers to help you design and build custom, high-quality, automated machinery. This is what matters to us. We are proud to offer an extensive catalog of cutting-edge robotic and mechatronic technologies, the combination of which is unique to Electromate. From the harshest conditions above or below ground to the highest accuracy and precision motion control applications, our solutions are unmatched in performance and value. No business is an island. There's no need to fend for yourself. Utilize Electromate's engineering expertise to complement your engineering team and get your product to market faster with less hassle. Our core purpose is to help manufacturers compete globally by building better machines using differentiated automation technology. This is our culture. This is our commitment to you. What's your core purpose? If you want to build a better machine, come talk to us. To learn more about what we have to offer, visit www.electromate.com today. Electromate provides motion control at the speed of technology,